Hello everybody, my name is Upia. I'm working under Dr. Jennifer Zernhill at the Energy Systems Institute. My research is on the characterization of rechargeable batteries, secondary batteries. I'm going to be talking about electrochemical cells, aka batteries. Um, the four that I chose to research were lead acid batteries, nickel cadmium, nickel metal hydride, and lithium ion batteries. I'll talk about the test methods that we did to prove our literature research, the results we got, and future endeavors. A primary battery, the difference between a primary and a secondary is that a secondary is designed to be recharged. Here in this picture, you can see the electrons go into the positive electrode, and this is a basic design of a battery, what's inside of the battery. You see the cathode and the anode inside the electrolyte, and this is what happens when you discharge any battery, a primary or secondary. Here is the charging of a secondary battery. As you can see, you can reverse. It's designed to reverse the chemistry reaction, so you're able to charge it. This is the chemistry behind the lead acid battery, and this is the lead acid battery that I was discharging and testing. These are the half reactions at the cathode and the anode. This is the nickel cadmium. This is the chemistry behind it. Here in the anode, you can see how the electrons are released when going this way, and when you reverse it, the electrons will go back. Here's the nickel metal hydride. In the nickel metal hydride, the cathode is metal hydride. The anode is hydrogen. It forms into metal hydride by hydrogen being absorbed into the metal. So you sort of like you're storing the hydrogen inside the metal. This is the lithium cobalt. Here you can see the lithium going from the anode to the cathode. And this is a general picture of a cylindrical battery. This is specifically a lithium ion, but most cylindrical batteries are designed like this. You have the cathode, a layer separating it, and the anode. This is some of the basic literature research that I did. Depending on the chemistry, the capacity and the voltage changes, and the internal resistance. This is a picture of the way we discharge the batteries. This is a lithium ion right here, a lithium cobalt specifically. This is the device we use to analyze the discharge curves of each battery. It'll plot the voltage as the battery discharges every second. So at the end of a discharge, we have a nice little graph that shows us what the voltage was at each second. We also did an internal resistance test. And the way we did it is we took a current shunt, or a very small resistor, and we connected it to the negative and positive sides of the battery. This way, we know the voltage we know the open circuit voltage of the battery, we know the resistance we use, and when we connect it, we measure very quickly the voltage across the resistor. With these knowns, we can figure out the unknown, which is the internal resistance. It's important to do this test quick because you don't want to shut out the battery too much, or else you might have permanent damages. This is one of the discharge curves of the lead acid. Here in this graph, it shows 3 different discharges. The red is the slowest discharge we did, and as you can see, as expected, you get the most capacity out of the battery when you discharge it slowly, as opposed to when you discharge it fast. The nickel cadmium performed as expected as well. The nickel metal hydride did not. This discharge is correct, but this one did not perform as expected, and I believe it's because before discharging it, we might have charged it too fast, which also affects the discharge curve. But can't be completely sure what the problem was. I'll retest it at 1 amp and other rates to see exactly if we can fix it or if there's a problem. And the lithium cobalt also performed as expected. It makes sense that the more amps you discharge it, the lower the voltage is. So right here, we discharged it at 2.6 amps. This one is at 0.52 amps. So you get less voltage, which makes sense. V equals I. This is the Ragone chart. It compares the power and energy of each chemistry. The red is the lead acid, and as you can see, per kilogram, it has the least amount of energy and power. The lithium cobalt, or the lithium ion, you see right here, it has the highest specific energy and power per kilogram. So if sizes are concerned, but you still want a lot of power and a lot of energy, you should consider the lithium cobalt. My future endeavors are to create one large chart of all the chemistries, or as many chemistries as I can of batteries, and just have a nice chart showing how they perform at certain rates, how they perform in certain situations. Also, I would like to study on how to optimize the batteries, how to get the most out of each battery. Like I said before, if you charge it too fast, it'll mess up the battery and things like that. Also, I want to study hybrid batteries. I was looking into combining some chemistries, maybe getting, and you're able to get a better battery, and looking into electric cars. What's the power in an electric car? I'd like to acknowledge CSTEP and the Energy Systems Institute. And these are my references. Any questions?
How did you decide on which batteries you were going to test?
Well, in our lab there's 3 of us, and after we decided we were going to study batteries, I was real interested in rechargeable batteries for something just like, this might sound a little dumb, but I was just really interested in rechargeable batteries because growing up, you play Game Boys, you play a bunch of games, and the battery is always, dying. I always figured why not just recharge the battery. So this is a good way to study it. And also in laptops, cell phones, there's rechargeable batteries. So wanted to look into it. And yeah.
Oh, you're going to continue? Or?
No, yeah.
Okay. Yeah, I really like that reason. Just one thing that I wanted to suggest to you is maybe you should just put that at the beginning, because I liked the presentation overall, but like an application was if you had like an application over there, that would be really cool.
True. Thank you.
What's the most commonly used secondary battery? Which one's the best one?
Depending on the application. Right now in cars, you'll see more lead acid than any other. For cell phones and laptops, you'll see lithium ion or lithium cobalt. So they're different. Depending on the application, you get different ones. The reason for this is because each battery performs differently. So in a car, the weight of the battery doesn't really matter. So you can use a lead acid. Any more questions?
So say I was buying a rechargeable battery. When I look for milliamp hours, is that how I rate a good battery? Or if I was looking at a secondary battery, which one to purchase? If I was going to use it something, how would I know which one is best to use?
Well,
what specifications should I look for? Like the amp hours or the voltage or?
that's a good question. I'd start off with what are you using, and then after you decide that, you decide is size important. If not, once you decide the size, you decide the chemistry, and yes, you do want the one with the most amp hours. The voltage doesn't really change across the chemistries, so like a lead acid, all the lead acids will have about the same voltage. So amp hours is good.